Alright guys, in the last video we left off with trying to figure out how to write the inverse of 2 to the x. We know that there is an inverse for 2 to the x because it's a one-to-one function. It passes the horizontal line test. But right now, we don't have any means of getting to the inverse function. So like at the end of the last video, I said this is where logarithms come in handy. Okay, so look, the whole goal is to solve for x. I want my equation to look like x equals something, okay? But right now, x is stuck in the exponent. I need a way to drop it down, but look what the logarithm does. A logarithmic function, right here, with base a, of course y is greater than 0 and a is greater than 0 and not equal to 1. That was in our original exponential video. If something is written as y equals a to the x, it is equivalent to log base a of y equaling x. See, if we rewrite it in terms of logs, if we apply this logarithmic function on it, we can drop this x from the exponent down to the earthly ground. All right, and then if we have something expressed in terms of y, if we have x equaling something in terms of y, we can now say that, for the most part, that this is our inverse function. So let's see how we can use this, okay? Let's look back to our example. So I have y equals 2 to the x. What I'm going to do is I'm going to take log base of 2. So there's like a little subscript of 2. Maybe I'll change the color so you guys understand what's happening. So this is like a function. I'm applying a function to this y, and I'm applying a function to this side, 2 to the x. And see this base right here? 2, log base 2, log base 2. This base can be any number you want, but I chose 2 for a specific reason. If I have log base 2, and inside my parentheses, I have an exponent with a base of 2 as well. So if these two bases are the same, I can actually just, in a way, you could think about like canceling everything out except for what's in the exponent, which is x. So if I have log base of 2, if I have log with a matching base here and here, I can just write what's in the exponent, which for us in this example is just x. So the inverse function for this guy looks like this. Log base 2, remember 2 is a subscript, of y equals f inverse of y. So that's our final answer right there, and I'll clean up that 2 for us because it looks really ugly. Boom. So the key takeaway here is that we chose log base 2 on purpose because we wanted this base to match this base in order for us to cancel out all of this stuff like that. And we're just left with the x after that. Okay. And that's what they say here. That's what this sentence is saying here too. It's the same exact thing. This is what we use to solve this question. Okay, so when you see a logarithmic expression, it's good to know how to rewrite it in exponential form. So for instance, if we're given something like this, 2 equals log base 3 of 9, log base 3, these parentheses mean of, and then 9. So if we have 2 equaling log base 3 of 9, how can I rewrite this exponentially? Well, what I'm going to do is I'm going to keep the base the same. See, this base right here will be the base of my exponent. So I say 3, and so the base will stay the same, but what I'm going to do is I'm going to kind of do a little flip. See, if this was x and this was y, I'm going to rotate their position. Boom, boom. So I'm going to have 3 raised to not the 9, but the 2 that was on the other side, and it's going to equal the 9. And that makes sense because we know that 3 squared equals 9. So in a way, if this was x, if 9 was x and 2 was y, I'm actually writing this guy in terms of 3y equaling x. Okay, so let's try this one more time. So here I have 3 equaling log base 5 of 125. So what I'm going to do is I'm going to rewrite this in exponential notation. So I'm going to keep the base the same. 5 will be my base, and instead of using x as my exponent, I'm going to use y as my exponent. So 5 to the third equals, and now I put x on the other side, 125. All right, so make sure you do this little loop-de-loop right here. They got to switch positions. And that makes sense because 5 times 5 times 5 is 125. So we did something right. That's great. Let's see what we have next. Ooh, okay, good. So now our goal is to use the concept that we just figured out to evaluate these logarithmic expression. What is log base 2 of 32? Well, just by looking at it, honestly, it confuses me. So anytime I see logs, what I do immediately, because logs can be very confusing and it's messy on the page, a lot of letters and symbols going around, immediately what I do is I rewrite it into exponential form. So let's write this in exponential form. I keep the base the same, 2, and I do the loop-de-loop with these two, right? I switch their position. So I have 2 raised to the y equaling 32. And now our goal is to rewrite 32, hopefully with a base of 2. So it might take us a second to think about it, but 32 can be written as 2 to the 5th power. Now, just like in our last video, because my bases are the same and exponential functions are 1 to 1, I can equate the exponent. So this tells me that y is equal to 5. Crazy, right? Like this example looks so complicated, so confusing. I feel like I would need to pull out a calculator, but we were able to solve it in 3 steps. So it's pretty useful to know how to go from logs to exponential notation. Let's do another one. Okay, we have y equals log base 3 of 1. Immediately, let's kill the log. I keep the 3 as the base, and I switch these guys around. I do a little rotation, right? So I have 3 to the y equaling 1. Now, how can I write 1 with a base of 3? Well, if you guys remember, how can I write 1 with the base of 3? Anything raised to the 0 power is equal to 1. So 3 to the 0 is equal to 1. So therefore, because I have common bases, I can use the 1-to-1 property and say that y is equal to 0. Right? I'm comparing just the exponents now. All right, let's see if we have another one. Hey, we do. Okay, so we have y equals log base 10 of 1 over 100. So let's see if we can get a little exponential notation going. So my base here is 10, and I'm going to switch these guys around, right? So I have 10 to the y equals 1 over 100. Okay, so I want to write 1 over 100 in terms of 10. The first thing I want to do is I want to get this 100 back on top. So the first thing I'll do is I'll throw a negative as an exponent. See, I brought that 100 from the denominator back to the numerator by giving it a -1 exponent. Now I have to think, how can I write 10 in terms, how can I write 100 in terms of 10? Well, 10 times 10 is 100. So I can rewrite this guy as this, y equaling 10 squared So I only manipulated that 100 on the inside of my parentheses. Right? I turned this 100 right here into 10 squared, and the outside parentheses was left alone. Last thing I'm going to do is this. Don't forget your rule of exponents, right? What is our rule of exponents here? If you have an exponent raised to another exponent, to simplify it, you just multiply them together. So I have 10 to the y equals 10 to the, what's 2 times -1? It's -2. Hey, we got the same base again. Same bases, meaning we can equate the exponents. So that means our answer is y equals -2. So as you can see, we're kind of just using the same rules over and over, switching from logarithmic notation to exponential notation, and using our one-to-one property to solve for the exponent. Okay, so here are some properties of logs that you should know. Log base a of 1 is always equal to 0, and that's what we had right here. Log base of 3 of 1, log base 3 of 1 was equal to 0. So log base a of 1 is always equal to 0. That's because if we were to rewrite this in exponential form, we have a to the 0 is equal to 1, which is true. Okay, for the next one, log base a of a is always equal to 1. Why? Because if we were to rewrite in exponential form, we can write a to the first power is equal to a. Well, that's definitely true as well. Okay, good. So the next two are kind of the most important ones. The next two are our one-to-one property and our inverse property. What does the inverse property say? The inverse property says that if you have log base a if you have log base a of a to the x, remember what we said in our first example? If you have the same bases, you can kind of cancel this whole thing out and you're just left with x. Same thing applies over here though. If you have log of, let's say, 2 to the x equaling, how do I say this without being too confusing? Like if you have 4, if I raise both sides, if I put this side in the if I put the left side in the exponent of 2, and if I put the right side to the exponent in the exponent of 2, then what happens is these two bases will cancel out, and I'm just left with x equals 2 to the 4th. So you'll see, we'll do more examples of that soon. And lastly, we have our one-to-one property, which is what we've been using. If log base a of x equals log base a of y, then x equals y, right? If you're using a logarithmic function with the same base, then the parentheses, and they're equal to each other, then the parentheses have to be equal. Whatever's inside the parentheses have to be equal to each other as well. Let's see. Did we do enough? We kind of did a couple of stuff. All right, so these are just two examples of the above. So this guy right here is using rule 2. Log base anything of 1 is equal to 0. Oh, sorry, that's not rule 1. That is rule 1, not rule 2. And then this guy, which one is this guy, would you say? I would say that's the inverse property, right? And we're following this one because there's 2 for the inverse. There's this one, and then there's this one. Because I have 2 raised to the log base 2, because these two bases are the same, I can cancel them out, and I'm left with just x equals x, which is true. Let's keep grinding here. So here's the one-to-one property. See, I have log base 3 and log base 3. If I have log with the same bases and they're equal to each other, that means whatever's inside the parentheses is also equal to each other. And that is this rule right here that we used. One-to-one property. And same thing goes here. I have log base 10 equaling log base 10 of something. That means whatever's in their parentheses have to equal each other. 2x plus 1 equals 3x. So we can solve for x, right? I can take I can take away 2x from both sides. And I'm left with 1 equals x. Alrighty. You know what? Let's just grind till the end here. Not much more to do. Okay, so now I've pasted 2 graphs here. This guy is a to the x. And this guy is log base a of x. This green one. And this line right here is y equals x. So what I want you guys to realize is because this is an inverse function, and we spoke about the graph of an exponential function, right? It has a horizontal asymptote at y equals 0, but it keeps growing and growing very rapidly. What I want you to realize is that inverse functions graphically are a reflection over this y equals x line. So you see, it's like if you were to turn your computer sideways so that this y equals x line is up and down, vertical, you could see that you could flip the blue line over the purple line to get to the green line, right? It's a flip over that line. So anytime you're dealing with inverses, it's always going to be a flip over this purple line. So this is when you have, this should be not 0. This should be, what? This is not y, a greater than 1. Sorry, there's always going to be a mistake in my notes. And this should be when a is between 0 and 1. So if it's some fraction between 0 and 1. So the same thing applies right here. This is a to the x. This is y equals x. And this is log base a of x. So a in this picture is some number that's greater than 1. So maybe like log base 2 of x or something like that. That's for this graph. For this graph, a will be something between 0 and 1. So maybe this is like log base, I don't know, 1/3 of x. I don't know why I drew double parentheses. Log base 1/3 of x. Okay, and the same thing applies if you turn your computer so that this purple line is vertical. You can see how the blue line reflected over this purple line gets you to the green line. And that's because they're inverses of each other. It's always true. The last thing we'll do for this part at least, and then we have one more sentence, is that we have to talk about the domain and range. So let's look at the blue line right here. And we spoke about this before. The domain for my exponential function, what are all the x's that I can put in? Well, the x's that I can put in for my exponential function, well, I can really put in any number I want. So I'll say it goes from -infinity to infinity. But what is the range? What are all the y values I can get out? Well, the lowest y value I can have is some number that's close to 0, but it's never 0. So it's 0 or greater. These are the y values I can get out from my exponential function. And it's the same thing if I go the other way around, right? So if I look at this graph right here, my blue function, my blue line, gives me the domain, which is anything I could put into it. I can put any number I want from -infinity to infinity, and the range, again, it will go from 0 to infinity. So the thing about inverse functions is that their domain and range are the flip of the domain and range of the original function. So if the domain of the exponential function is -infinity to infinity, that means this will be the range of the inverse function. Also, if the range is 0 to infinity, then the domain is 0 to infinity. See how they flip it around, right? They switch spots because they're the inverses. And the same thing goes here. If the domain for this guy is -infinity to infinity, then it's the range. The domain is 0 to if the range is 0 to infinity, it's the domain for this guy. So again, because they're inverses, the domains and the range switch spots. Okay, so the last thing we're going to talk about here is this. In all of our examples, we were talking about log base A of something. Now, if you ever use a scientific calculator, you'll never see something like this. You'll never see a base A. They'll never ask you to put in a base of A. So why? What you'll see instead is this. You'll just see a button that says log of x. Well, anytime we see log of x, it's just like an implied version of A being 10. So anytime you see log of x, it really means log base 10 of x. And the other thing that you'll see a lot on the calculator is this thing right here, ln. ln of x is just log base, remember we spoke about this in a couple of videos, e, Euler's number of x. So just know that whenever you see ln of x and log of x, don't get freaked out. It's the same thing. We're still just talking about the big picture, which is log base a of x. All right, he's what we're trying to focus on. But for ln of x, our base is e, and just a pure log, the base is 10. All right, so we'll do more of this in the next video. I know this is a big chapter and we still got a lot more to go. So be patient, guys. I know it's hard to do this remotely.